This is the third and last of the 3 videos that will try to serve as a replacement for the class that we lost to the bomb threat. This one's about Euler-Lagrange equations, which historically are the oldest of all the topics we're considering in this course. Euler discovered this way back in the 18th century. A norm space we haven't had much occasion to consider is the space of differentiable functions, defined on the closed interval from t1 to t2. On this space, the norm is defined as the maximum absolute value of the derivative, but it's conventional to add on to that the maximum absolute value of the function x of t itself. Otherwise, a constant function that was non-zero would have zero norm. With this definition, it has non-zero norm conforming to the general requirement of a norm. But we don't really need this norm at all. Leuenberger comments that the differential is actually Fréchet, and in order to make that comment, he needs a norm in the domain space. Euler, who lived centuries before either Gateau or Fréchet, and who didn't really have any sort of sophisticated modern grasp of real analysis, would not have understood this statement in the slightest. Okay, we want to build a functional on this space. That is, we want to take a differentiable function and define a way of turning it into a real number. And the way we're going to do this is to introduce a continuous function of 3 variables, which are conventionally denoted by x, v, and t, with the idea that x is position, v is velocity, and t is time. And we're going to require that this function has continuous partial derivatives with respect to its first 2 arguments, x and v. So here's a sample of such a function. Square v, subtract off the square of x, and add on the absolute value of t. Notice the partial derivative with respect to the third argument is not defined at t equals 0. That doesn't bother us. Now, pick any vector x of t in this space D. Once we know x of t, since it's a differentiable function, we can calculate its derivative, x dot of t, and we can substitute in x and x dot in the first 2 slots for my function f, substitute time itself into the 3rd slot. This whole business is now a function of time in 3 different ways: directly, indirectly through x, and indirectly through x dot. But it's a function of time. We integrate it from t1 to t2. We get a real number. And I'm going to symbolize that nonlinear functional by j. Here's an example. I could pick my interval to go from 0 to pi over 2 and use the function I calculated before. So if x of t, my vector, is sine t, x dot of t is cosine t. When I plug into x, I get v squared, which is cosine squared t, minus x squared, which is sine squared t, plus the absolute value of t. That's cosine of 2t plus t, because t is not negative on this interval. And when I integrate, the integral of cosine 2t on this interval is 0, but I do get 1/2 times pi over 2 squared from the last term. All that matters about this is I took a vector, x of t, and j produced a value that was a number. Now, usually we insist that x has specified values, both at t1 and at t2, and we want that to persist when we add on our alpha times h of t, which means that h of t has to be 0 at these endpoints. Here's a nice way of visualizing this. you take your vector x of t, add on some small increment alpha times h of t. Historically, this is known as the variation, and this subject is called calculus of variations. And here is x of t plus h of t. And to say that the Gateau differential is equal to 0 at x is to say that no matter what differentiable h of t equal to 0 at both t1 and t2, you add on the rate of change with respect to the amount of that alpha that you add in is equal to 0. Now let me show you how to turn that into a differential equation. This is the only proof from this outline. It's the derivation of the Euler-Lagrange equation. And it looks messy, but it's actually remarkably easy. So here's the functional whose extremum we want, the j from the previous slide. And the first thing we've got to figure out is its Gateau differential. Well, that just involves a definition. The Gateau differential of j evaluated at the vector x0 for the variation h, and both of these are vectors, so they're functions, is the derivative with respect to alpha, evaluated for alpha equal to 0, of f of x plus alpha h, and therefore the second argument has to be x dot plus alpha h dot, and the third argument is just t. You say, hey, what about subtracting off f of x from f of x plus alpha h? That's all taken into account in the definition of the derivative. Remember, you take the difference between two function values, divide by alpha, and take the limit as alpha goes to 0. That's what we mean by d by d alpha of that. Now, what happens when we change the two arguments of f from x and x dot to x plus alpha h and x dot plus alpha h dot? Well, for any specific value of t, whereupon everything in question is just a number, we know how to do this. We take f and take its partial derivative with respect to its first argument and multiply that by h of t. The alpha disappears because we're taking this derivative. And for the second one, we take the partial with respect to x dot and multiply that by h dot. This is just the chain rule for the composition of two functions, one of which is a function of three variables and has partial derivatives that are non-zero with respect to two of them. Now comes the tricky part. Here we've got an h, here we've got an h dot. That's not very satisfactory, but we can fix it. We can integrate by parts, can't we? So we integrate by parts, setting dv equal to h dot of t dt, whereupon v is just h of t. And when we do the integration by parts, we're going to get a u times v term, but that's going to go away at both endpoints because v is equal to 0 at both endpoints. What about u? Well, the other factor is the partial derivative of f with respect to its second argument. du is what we get by differentiating that with respect to t. So it's d by dt of this partial derivative. And notice, for once, the dependence of f on t may actually turn out to be significant, because what we're saying is plug in x of t and x dot of t. This whole business is then a function of t. Take its derivative with respect to t. Now, having done that, we can combine our two integrals into one because we've got a factor of h of t. We get a minus sign from the integration by parts rule. The uv term, as I said, goes away because h is 0 at both endpoints. And let's give this function a name. Let's call it g of t. This has to equal 0 for all values of h. And if this function is a continuous function, the only way that can happen is for it to be identically 0. Let me give you a proof of that. Suppose g of t is a continuous function that is different from 0 for some value t0 of its argument. Then, since it's continuous, there must be some interval surrounding t0, going from t0 minus delta to t0 plus delta, when it's nice and close to its value at t0. I might, for example, as my epsilon, choose g of t0 divided by 2. What about h of t? Well, I'll set h of t equal to g of t on that interval. I'll set it 0 everywhere else and fiddle around a bit. I suppose I really should make it into a continuous function, but that's not going to affect my argument. Clearly, on this interval, I will have the square of that function. It will be a positive quantity, and its integral will be different from 0. So the only way that we can get this integral to equal 0 for all h is if this term is 0. Setting this term equal to 0 gives us the famous Euler-Lagrange differential equation. And when we hopefully have a real live class on Wednesday, I'll start showing you examples of how you can use this differential equation to solve some otherwise remarkably intractable looking problems.